In this question, we are given a network of roads. The number on each arc represents the length of that road in kilometers, and we have to use Dijkstra's algorithm to find the shortest route from A on the far left to J on the far right. After we've done that, we must state the route itself and the length of that route. For a Dijkstra's algorithm question, in an exam, you'll always be given a blank diagram similar to this. Usually in an exam there'll be a key reminding you what each part of these boxes represents. On this one there wasn't a key, so here's a reminder. The bottom cell is for our working values, and that's the numbers that we keep updating as we work through the algorithm. This cell here is for the order in which we label the vertices, and the top right hand box, that one there, will represent for each vertex the length of the shortest route from that vertex to the start. And in this question the start is A. And because A is the start, the first thing we do is put a 1 in there and put a 0 there. The 1 because A is the first vertex to be labelled, and the 0 tells us something fairly obvious, but it tells us that the shortest route from the beginning, which is A, to this vertex, which is also A, is 0 as we'd expect. That's how we always begin. Then we look at where can you travel to directly from A. We could go direct to B, and the length of that journey would be 0 plus 17, which is 17. So we put that in our working values box. If we travel directly to C, that would have a journey length 18, straight to D, journey length 15. Those are our working values. Now that we've done all the possible direct journeys from A, we need to choose the smallest of all working values. Out of 15, 18 and 17, clearly 15 is the smallest, which means D is the second vertex to be labelled, and its current working value becomes its final value in the top right hand box. That 15 is telling me that the shortest route from the beginning, which is A, to this vertex, which is D, is 15. So we're not going to find a shorter way of getting from A to D than length 15. After you've labelled a vertex, you must then look and see where could we travel to directly from D. Well, we could go direct to F. And the length of that journey would be 15 plus 14, which is 29. That's the working value that must go in that box. Or we could travel directly to I. Length 15 plus 29, 44. Those are the only two vertices we could travel to directly from D. We wouldn't travel back to A because A has already been completed. We now must look at all of the working values and choose the smallest. Don't just look at the last two we wrote down. We must look at all of them. And clearly the smallest of all the working values is 17, which means B gets a final value of 17, and A was the first, D was the second, so B is the third vertex to be given a final value. 17 tells me that the shortest journey from the beginning to B has a length of 17. Same thing as after we'd labelled D, we now look where can we travel directly from B. If we went to G, that length would be 17 plus 27, which is 44. Or I could go to E, which would have a length 35. We're back to looking now at all of the working values of vertices that haven't been given a final value. So I'm not looking at 17 anymore, I'm not looking at 15 anymore, because D and B, they've been labelled. I am looking at 18, 35, 29, 44, and 44. Clearly the smallest is 18, so C gets a final value of 18, and if B was the third, C will be the fourth to be labelled. From C, we could travel directly to E. That length would be 18 plus 15, which is 33. And because that's smaller than 35, then we cross out the 35 and put a 33. The examiner will be looking for things like this, in particular, updating an old working value with a new, smaller one. That's evidence of a correct application of Dijkstra's algorithm. Also, inside the box, the order in which these numbers are written is also important. So we must have 35 on the far left, and then after that 33. There might be more numbers to go in this box yet, in which case it will go after the 33, and so on. So that's traveling directly from C to E. If I did directly from C to F, 18 plus 10 is 28, which is smaller than 29. So we update that working value and it becomes 28. Those are the only places I can go directly from C. So I'm back to looking at all the working values of the unlabeled vertices. So not A, not B, not C, not D. I'm looking at E, which is 33, F, which is 28, G, which is 44, and I, which is also 44. The smallest of those is clearly 28. So C was the fourth, which means F is the fifth to be given a final value, which is its current working value, which is 28. From F, we could travel directly to H, so that length would be 45. Or we could go to I, length 41, which is smaller than 44, so we update the working value. A common error here would be to miss the direct journey from F to E. E has not been given a final value, so it is something we must include. F to E would be a journey 28 plus 4, which is 32, which is smaller than 33. So again, we update the working value. It's now 32. What that means is we've just found a quicker way of getting to E than the previous quickest, which was 33. Now there's no other vertices I could go to directly from F. I've got all three of them. So now, once again, look at all the working values, and the smallest of those is 32. F was the fifth, so E is the sixth to be given a final value, which is 32. From E, I could travel directly to G. 32 plus 6 is 38. Or H, 32 plus 12 is 44. Both working values got updated. From E, I can't go to F. F has already been given its final value. So there's only G and H. Looking at all the working values of the unlabeled vertices, I can see the smallest is 38. E was the sixth, so G is the seventh to be given a final value. From G, I could only travel directly to J, which has length 53. I could go to B, but B's only been labelled. I could go to E, but E's already been labelled, so it's only J. So J that hasn't. Looking at working values, the working values of the unlabeled vertices are 44, 41, and 53. Smallest is 41. So I becomes the eighth to be labelled, which is 41. Now from I could travel directly to H. That is possible. H has not been given a final value. 41 plus 3 is 44, which is the same as the current working value at H. So I don't need to write another 44. I only need to write it down if it's smaller than the current working value. So I'm not going to write it down. 44 is the same as the one that's already there. From I could also travel to J. 41 plus 13 is 54, which is longer than 53. So once again, I don't have to write it down. We're only interested if it's smaller than the current working value. If you did write it down, then I'd recommend putting it in brackets just to show that actually we're not interested in that number because it's bigger than the 53 we had first. I think the quickest thing is just to not write it down. Of the working values, and there's only two of them at the moment, there's 44 and there's 53. 44 is the smallest, and because I was the 8th, H is the 9th to be given a final value. From H, the only place I could travel that hasn't been given a final value is J, which would be 44 plus 11, which is 55. Again, that's longer than the current working value, so we're not interested, which means now there's only one working value at a vertex which is unlabeled. So 53 is the smallest because it's the only one. So J gets a final value of 53, and J is the 10th to be labeled. We've got most of the marks here in part A, and there were 5 marks available. I just need to now finish off by writing down the length of the shortest route and finding the route itself. So the length is easy. It's the final value of the final vertex, J. So the length is 53. I think the units were kilometers. Yep. So 53 kilometers. The route itself takes a bit more working out. To find the route, we need to work backwards from the end. And I'm looking at the final values of J, G, H, and I. And I'm looking for any instance where if I subtract the final values, it is equal to the length of the edge between them. So down here, 53 take away 41 is not 13, so we're not going to travel along that edge. Here, 53 take away 44 is 11. Sorry, no, it's not. 53 take 44 is 9, not 11, so we're not traveling along that one. This one, however, 53 take away 38 is 15, so this edge, G, J, is part of the route. Because J was the end, I'm going to write that one last. And we must have travelled along GJ, so G must have been visited before J. We continue doing that, finding the edges where the difference is equal to the difference in the final values is equal to the edge. Up here, of course, 38 take away 17 is not 21, so it's not that one, but the other one does work. 38 take away 32 is 6, so we do travel along EG. So we visited E before G. From E, looking for the correct edge, and there's 3 possibilities here. 32 take 17 is not 18. 32 take 18 is not 15. But 32 take 28 is 4. So it's that one. So we must have visited F before E. F, doing the same thing, we must have been at C before F. And before C, we must have been at A. It's A, C, F, E, G, J. And let's check that. A, C, F, E, G, J is the route which has this shortest length of 53. And that's the end of this part of the question.